fractions is a process in mathematics that later on in other courses can help us a great deal when we're trying to do certain operations. In calculus, when you're integrating functions that are rational functions, it's easier to do the integration if we have our expression as fractions written with the lowest power denominators possible. And so if we have a fraction that has higher power denominators, then we want to make sure that we can split it back up as separate fractions that were added or subtracted to overall in the end process be the same as the original fraction that was in the problem, and then be able to do the integration process. And there are other places as well where partial fractions can come into play. Since most of the work done in the process of the partial fractions is an algebraic method, we study the idea of partial fractions now, and then later on can apply that to when we need it in further coursework. So before we go on with what specifically is done with partial fractions, let's back up and think about what we did when we had rational expressions added together and how we went through doing the addition of those in algebraic form to get an overall sum or difference of two fractions. So suppose, for example, that we were taking 5 over x minus 3 and adding it to 2 over x plus 4. And we wanted to start by just adding these. And here we're just going to recall this to help build the process of what we do in partial fractions. Well, remember when adding fractions, we have to have common denominators. So we look at the two different denominators. They can't factor any further, and the lowest common denominator would be what we would need to build towards so that whatever we had as an algebraic expression, each of these denominators would divide evenly into it. Well, remember the length of a fraction bar is a grouping symbol, so I have a quantity x minus 3 in the first denominator, and it doesn't factor any further. And I have a quantity x plus 4 in the denominator of the second fraction, and it doesn't simplify any further. So my lowest common denominator is x minus 3 times x plus 4. Now, in order to add these fractions, I need to build each fraction so that I get the lowest common denominator. So for my first fraction, I need to build that fraction top and bottom by the x plus 4. And then for the second fraction, we need to build that fraction top and bottom by the x minus 3, the factor that it doesn't have yet. Now, also recall in working with adding or subtracting fractions, once we build to get the common denominator, we want to multiply out the numerator expressions and then be able to add the numerator but keep the common denominator. So I'm going to multiply out the numerator but keep the denominator factor. So this is going to be 5x plus 20 and then plus 2x minus 6, and that's all over the x minus 3 times the x plus 4. So then when I combine my like terms in the numerator, remember we look at like terms by the variable expressions to the same power would be like terms. So 5x plus 2x is 7x, and then the plus 20 minus 6 is plus 14. So this fraction, 7x plus 14 over the x minus 3 times x plus 4, is the sum of these two algebraic fractions that we started with. Okay, so here's the thing with the partial fractions. If I was trying to do the process in calculus or later on in other topics where this was the original fraction that was involved in the problem, and the process needs me to have it back as the individual fractions that were added or subtracted to attain this, then what I need to do is figure out how I can go from this 7x plus 14 over x minus 3 times x plus 4 and split it back up and figure out what the fractions were that were added or subtracted to get that. So I actually need to just put like placeholders in for what the ultimate numerators would be, and then go through the process just as we would have if we knew those numbers, and then figure out what they are. So that's kind of where we have done the process to start with. Now if we were starting to do our partial fractions, and the question actually asks us to decompose this 7x plus 14 over x minus 3 times x plus 4. Into partial fractions. It's actually asking me to get those individual fractions back. Now, not only could they have written my original question with the factors in the denominator factored out, they may have actually even taken it all the way back where that might have been multiplied out. So the denominator might actually have said x squared plus x minus 12, in which case I would need to factor it first before I got started on the process. Now we want to write this as partial fractions with the lowest power denominators possible. So what we look at in the denominators is there's like different stages that we have to pay attention to. So if the individual factors were only to the first power and none of them like overlapped, and I was able to get them down to degree 1 within each factor, then I want to take it down to where one of the factors and the other denominator is the other factor. Certainly if you had 3 factors, you'd have to have 3 different fractions with your denominators as you go. Now as we work through this, there's a couple other cases that we'll do examples for. If I have a factor that's to a power that's higher than just 1, we're going to have to go through a process to compensate for what would occur then. Or if I had a denominator that was quadratic and it didn't factor any further down, how you would handle the setup for that type of problem. So they will come later on in this video. But for now, let's just work with the one that we had started with here. All right, now I need placeholders in the numerator, and I want to ultimately have it where those are numbers, and I don't want to get them confused with the variable that's really in the problem. So since the variable in this problem is x, and I just want placeholders, I'm going to use letters from the beginning of the alphabet to be these placeholders. And I'm just going to start with the first letter of the alphabet, A, and then work my way down as many of the letters that I need to have. And I'm just going to do them with capital letters to just kind of accentuate where my focus needs to be. So we're going to have a placeholder for the numerator for the first fraction, A, and after A comes B, so placeholder in the numerator of the second fraction to be B. Now since my denominator was first degree, then the degree less than first degree is degree 0, so there's no x's next to these. Okay, so that's the setup of it. Now I just go through the motions I would do if I had the original problem with the numbers in the numerator and work down. So we're adding, so we need common denominator. The common denominator between x minus 3 and x plus 4 is x minus 3 times x plus 4. So my first fraction already has the x minus 3 factor. It needs to be built by the x plus 4. And the second fraction already has the x plus 4, so it needs to be built by the x minus 3. Now I'm going to do the next stage where I multiply through the numerators but keep the common denominator. So this will be ax plus 4a plus bx and then minus 3b, and that's all over my x minus 3 times x plus 4. And then I want to put this in descending order with respect to the powers of x. And then any term where it has more than one term that has that power of x, I'm going to factor the x power out. And I'm going to factor it out the back. So here I would have ax, and then I'll write plus bx, because they have the same x to the same power. And then plus 4a, and then minus 3b. And then the terms that have the x, I'm going to factor the x out the back. So we are going to have a plus b times x, and then plus 4a minus 3b. And that's all over x minus 3 times x plus 4. Now, this fraction is combined, and it is in the descending order of x in its numerator. But I want this fraction to be the exact same value as my original fraction, only having the correct numbers in the numerators. So what you do here, you have to take and look at the coefficients in front of the powers on your x, and the coefficients there have to equal the coefficient in front of that power of x in the original problem. And then the constant term that doesn't have an x has to be equal to the expression that doesn't have an x multiplied to it in this buildup. So our a plus b is in front of the x, that's a coefficient in front of x, and 7 is the coefficient in front of x. So a plus b has to equal 7. And 4a minus 3b has to equal 14. And I want to solve that system. If you don't remember how to do that specifically, just watch some of the videos that I'll have put into the description in this video, where you can link to it and then see how to solve a system of equations. But this is just a system of linear equations in a's and b's, just like when you have a system of linear equations in x's and y's. I just want to find a and b here instead of x and y there. So we have our graphing, elimination by addition, substitution. If you've gone further on in the process of studying about your solving of systems of equations, there's the matrix methods, the Gauss-Jordan elimination, Kramer's rule, matrix inverse method, all those different methods that you could choose from in order to solve this system. Now here, my coefficients in front of my b's are already opposite in sign, and the coefficient of b in the first one is just a 1, so it'd be really easy to solve this by elimination by addition, by just multiplying this first equation through by 3 and then adding the equations. So multiply your first equation through by 3 and you'll get 3a plus 3b is equal to 21, and we're adding that to 4a minus 3b is equal to 14. And when we add them together, 3a plus 4a is 7a is equal to 21 plus 14 is 35. And so when I divide both sides by 7, I get that a is equal to 5. And once I see that a is equal to 5, I can put that in for a in the first equation. 5 plus b is 7, so subtract 5 from both sides, b is equal to 2. So then what we get is writing out what our solution is by putting these numbers in the numerator. So decomposing this original fraction into partial fractions gives me, well, a is above the x minus 3, so it's 5 over x minus 3, and then plus 2 over x plus 4. So those are the fractions that were added together to create that. Now we were doing this in terms of recalling the old process and then going backwards on it. Remember, if it says to just combine these fractions or perform the operations or whatever, then you automatically know you're building to get your common denominator and adding them or subtracting them if that's the operation that's between them. It's when they give you the overall solution or the overall sum or difference of fractions, and it asks you to decompose that into partial fractions, that you go this way with it. But just kind of looking back, we see over here 5 over x minus 3 plus 2 over x plus 4. We did get back what we started with when we had gone through and we added them together. Okay, now we're going to go through and look at some other examples. Now let's look at another example of doing the partial fractions process. So here it wants us to decompose 3x minus 23 over x squared plus 2x minus 3 into partial fractions. So I first compare the numerator and the denominator. The numerator needs to be smaller degree than the denominator, and if it's not a smaller degree than the denominator, then you need to do long division to divide out the quotient part and have that listed first, plus, and then the partial fraction work after that. So the degree of the numerator is 1, the degree of the denominator is 2, the numerator's degree is smaller than the denominator's degree, so I'm going to do partial fractions on the, what I have without having to do the division part first. Next up, the denominator is not factored, but it is factorable. So when I look at this and getting started with it, it's 3x minus 23 over the factorization of x squared plus 2x minus 3. Well, the leading coefficient's 1, and the factors that multiply together to make negative 3, who when you add them together get positive 2, are positive 3 and negative 1. So this is x plus 3 times x minus 1. Now, I look at these denominators. I was able to get them down to factors that are degree 1, and none of them have a power that's higher on it. None of them repeated is the factorization in the process that I worked. So I have this where I'm going to break it up as partial fractions of a over the x plus 3 plus b over the x minus 1. Now here I want to stop for a moment and say that we always put a plus between here. If it needs to be a negative number for whatever it has to work back out for the numerator, b will have the correct sign it needs to have. So even though there's a minus in here, that doesn't affect how you attach the partial fraction setup when you're getting ready to work with it. Okay, now remember we go through the process of building the fractions to get the common denominator. My denominators are x plus 3 and x minus 1. So the first fraction needs to be built by the x minus 1. And the second fraction has to be built by the x plus 3. Okay, now remember when we're at this stage, we want to remove the parentheses in the numerator, do the arithmetic across the numerator, and keep the common denominator. So this is ax minus a, and then plus bx plus 3b. And that's all over the x plus 3, x minus 1. We look at these term by term. We find the terms that have the same power in x, and then we put them next to each other and factor the x out of the back. So this will be ax plus bx would be next to each other, and then we factor the b out, we factor the x out, and so that gives me a plus b times x, and then that leaves with minus a and plus 3b. That's all over x plus 3 times x minus 1. And then we equate the coefficients in front of the different powers of the variable with the corresponding coefficients in front of the variable from your start problem, and equate the part that doesn't have any variable multiplied to it, and that gets equated with the constant from your problem. So we're going to have a plus b has to equal 3. and we have that negative a, don't lose that minus. So negative a plus 3b has to equal negative 23. Now, I solve this system of equations by either graphing, substitution, elimination by addition, Gauss-Jordan elimination, matrix method, inverse methods, Kramer's rule, all those different options of ways to solve a system of equations. This one is perfectly suited for elimination by addition because the coefficients in front of your a are already opposites. They're not only opposite signs, they're opposites of each other. The coefficient in front of the a in the first is 1, and the coefficient in front of the a in the second equation is negative 1. So now when I add these together, a combined with negative a, the a's cancel. B plus 3b is 4b. Positive 3, and then combined with a negative 23 is a negative 20. And now I've eliminated the variable a. I'm ready to divide both sides by 4 to solve for b. And I get b is equal to negative 5. And now that I know that b is equal to negative 5, I put it in either of these original equations to find a. So I'm going to put it in the first equation, a, and then remove the b and put in negative 5. So a minus 5 is equal to 3. And then add the 5 over, I get a is equal to 8. And so my partial fractions that mean the same thing as this original rational expression is, okay, a is 8, and a I set over my x minus 3. So I have 8 over, x plus 3. And then my b is negative 5. So I could write this as plus negative 5 over the x minus 1. More likely you're going to see it then as written as minus 5 over x minus 1. So there you have your partial fraction decomposition for this original rational expression. And again, the goal is to write it as sum or difference of fractions whose denominators are the lowest possible power that we can break it up into. Let's see another example. This next example, we want to decompose 3x squared plus 8x plus 11 over x plus 1 times x squared plus 2x plus 3 into partial fractions. Now, if you had thought about what would be the highest power if you multiplied out the denominator, you don't want to multiply it out, but just think about what your highest power would be. Well, x times x squared would be the highest power from the first parenthesis grouping times the highest power of the second parenthesis grouping, so that would be an x to the power 3. My numerator's highest power is x to the highest power of 2. So since my numerator's degree is smaller than the denominator, I don't have to do the long division prior to setting up the partial fractions. So remember, if that numerator's power is higher or the same as the denominator's highest power, then you need to divide out the quotient and state that plus then whatever you get for your partial fractions. But we're good to go on that. Now the denominator has been factored, and I look and this first factor is to the highest power of 1. The second factor is to the highest power 2. And I'd rather have that down to be linear if I possibly could. But when I look at this, the factors of 3, there's no factors of 3 that would add to get 2. Because 1 and 3 are the only factors of 3, and 1 plus 3 is 4. So I can't factor that quadratic any further. So I'm stuck with that being quadratic. But there is a theorem in algebra that says all polynomials can be factored down to linear and quadratic factors. Says it can happen. Sometimes it's tricky to figure out the factorization, but they all can be. So the highest power you're going to get stuck with as a denominator factor is your power of 2. Now the setup is a little bit different when you have a factor in the denominator that's quadratic and doesn't factor any further. So I'm going to have my fractions. One fraction is going to be the x plus 1, and the other fraction's denominator is going to be the x squared plus 2x plus 3. And when my denominator's fact is a highest power of 1, the numerator is just a constant, so I just put the a up there, because a 0 degree is the degree less than the first degree. If I have a quadratic that I couldn't factor any further, then its numerator could have a first power term as well as a constant term. So I have to put placeholders for both of those situations. But I keep wanting to go down the alphabet for the placeholders. So after A comes B, and B would be the coefficient in front of the x, and then C would be the constant term. So you have to leave a placeholder for either of those occurrences. Once I figure out that that's how the setup is, I go back through the exact same process I did before in order to figure out how to break it into the partial fractions. So remember, next we build to get the common denominator. So I need to take this first fraction and build it top and bottom by the x squared plus 2x plus 3. And then I need to take the second fraction and build it top and bottom by the x plus 1, the other factor it doesn't have. Now remember, at this stage we multiply out the numerators but keep the common denominator factored. So this will be ax squared plus 2ax plus 3a, and then here it's a binomial I have to FOIL out and then add that. So plus bx squared plus bx. So first, outer, inner is plus cx. And then last is plus c. And that's over the x plus 1 times the x squared plus 2x plus 3. Now remember, the next step, we want to get all the terms that have the same power of x next to each other and factor that power of x out the back. So we have an ax squared and a bx squared. So I'm going to write a plus b and then times x squared. And then I have a 2ax, a plus bx, and a plus cx. So I go plus, and think about factoring the x out the back. So that's 2a plus b plus c all times x. And that takes care of this term, and that term. And then I have 3a plus c. So plus 3a plus c. And that's all over the x plus 1 times the x squared plus 2x plus 3. All right, now we're going to equate these coefficients in front of the degrees or the powers of our factors with the x's, the terms with the x and the powers. And we're going to equate them with the coefficients from the original problem. So a plus b has to be the same as the coefficient in front of the x squared. So a plus b has to find the x squared, see the coefficient is 3. A plus b has to equal 3. Then 2a plus b plus c has to equal 8 because they're the coefficients in front of x. And then 3a plus c has to equal 11. So that's what we need to have in terms of our system of equations to solve. Now, when we're looking at solving the system of equations, again, we can solve this by substitution, elimination by addition, by Gauss-Jordan elimination, by matrix inverse method or by Kramer's rule. So let's solve this just by elimination by addition. Now, by elimination by addition, we want to eliminate one of the variables from the equations taken two at a time. So let's say that we wanted to eliminate the b variable. So my first equation and my second equation, if I look, they both have b's, and if I just multiply the first one through by -1 and add it to the second equation, that'll get rid of the variable b. So we're going to go -a minus b is equal to -3, and add that to 2a plus b, then plus c is equal to 8. And when I add them, I get a plus c, because the b's cancel, is equal to 5. Now, normally in a process, I would also take this third equation, which we haven't used yet, with either of the first two equations and do my multiplication to still get rid of the b. But I picked the b specifically here to get rid of because I noticed that the third equation doesn't have a b anyway. So I can just bring that equation, that a plus c is equal to 5, and the 3a plus c is equal to 11, and solve that system. This would be really easy to solve by elimination if I multiply the first equation by -1, because then the c's would cancel. So I'll just multiply through by -1, and that gives me -a plus 3a is 2a. The c's cancel, is equal to 6. Divide both sides by 2, and I get a is equal to 3. And now once I know that a is equal to 3, I can put the a in any of the actually original equations, let's do it that way, and find other remaining values. So, well, actually I should take it to one of these intermediate ones. So since a is equal to 3, then 3 plus c is 5. Subtract the 3 from both sides. C would be 2. And then when a is 3, c is 2, I can put that in any of the three original equations to get b. Any of the three original equations that have b. So in my top one would be easy to put in the 3 for my a. Then 3 plus b equals 3, so b is equal to 0. So what that means then, for my partial fractions, I have a is 3, so that's 3 over x plus 1, plus b came out to be 0, so I don't need to write that term because 0 times x is just 0. So in this case, it doesn't have that x term in the numerator, but I had to put a placeholder just in case. And then the c came out to be 2. So when I have 0x plus 2 in this numerator, it's just going to be a numerator of 2 over the x squared plus 2x plus 3. So there is your setup and your final solution of the partial fraction decomposition of that original fraction. And then another example is if I have a repeated factor. With a repeated factor, like say you have an x minus 1 to say the power 3 in the denominator, then you need a denominator of x minus 1, another denominator of x minus 1 squared, and another denominator of x minus 1 to the third. You have to build up on powers of that denominator until you get to the highest power that it had in its factorization. But that should get you to the different examples and then be able to break your overall fraction up into the partial fractions if that's a required process in a concept that you're dealing with at that time.